Swayam Prabha. Digital India. Educated India.
So yesterday we saw the simple matrix addition algorithm, just swapping of the loop can actually make the algorithm run much faster, while the other way it can kill performance. Okay, so these are some very small but very important subtle integrities that we need to keep, subtle details that we need to keep in mind when we write compilers, and this type of a knowledge will come only when you have this global view of how an system is organized. Okay, so that's the most important one. So just learning organization in isolation will not serve any purpose. So this is one very interesting stuff. So let us now go and start. So what is the challenge in this whole cache organization, right? So let us see, there is a RAM, okay, there is a front side bus, and there is a CPU, and here is the cache. Okay. Now when I want to read a location, I fetch it from the RAM and put it in the cache, and I keep accessing it. Now what is the problem here? What could be one very important problem? Program will not write, so the CPU will only interact with cache, it will not go there. So yes, so this problem of what he said is called cache coherency problem. Okay. I fetched something, here it was some 15, I fetched this, it was 15 here also. Now I changed it to 20, when will I change that to 20? So there is a difference. So for a given memory location, please understand that there are two versions of values that are stored, one in the memory, one in the cache, correct, right? So if I touch this, if I change in the cache, then the version that is stored in the cache is different from the version that is stored in the memory. Okay, so there is a difference, right? The latest value will be always in the cache, while the the older value can be there in the memory, right? So this difference is basically called the cache coherency problem, right? As far as I have only one processor, this cache coherency is not going to be a big issue for me, because always I am going to read from the cache, and if it is there in the cache, anyway I am going to get the latest value. But when I go to multi-cores, where I have 4 cores and they are all sharing a memory, then there is going to be an issue. We will come to that when we address multi-core memory organization, which will follow, say, from next Monday. Okay. So cache coherency problem is addressed in two ways. Traditionally, there are the solution to cache coherency forms the basis of classification of a cache, right? So that is based on just addressing cache coherency, cache is classified into write through caches and write back caches. Okay?
Is this problem when two processors are trying to access the same?
No, only one processor. But when two processors start accessing, so you have a cache, I have a cache, you have taken 1000 from the memory, some location 1000, and you go and change that value. I am trying to access 1000, you have that 1000. I don't have access to your cache. So these type of problems will come. Very interesting, and I will tell you some simple protocols of how to handle it. We will discuss this as we go through the next part. But now, just a single processor. Now still there is a cache coherency still exists. There are two versions of the same memory, one in the memory itself and another is the another in the cache, and both carry different values. But one thing that we should notice, the latest value is always in the cache. Now based on how to handle this coherency problem, caches are classified into two, write through cache and a write back cache, right? In a write through cache, when I write into a location, I also go and immediately update the memory. So when I change this to 20, I also immediately go and change to 20 here. Okay. In a write back cache, I only change this, and whenever this is evicted, so this word evicted is used. Evicted means that something else collides into this, and so I have to throw it off, meaning I am evicting now. Whenever I am evicting it, I have to go and write. write it. So this is write back, or this is also called delayed write, or so many names, lazy write, okay, so many names, lazy write protocol, nothing, same story, okay. So this is, right, so do you get this, right? So I write back, in the case of write through, when I change this location, immediately I will go and change in the memory. The biggest disadvantage of write back, write through is then I do not actually enjoy the speed of the cache access. Every write is equivalent to a original memory, it is as if whether the cache existed or not, right. It does not matter, because every write I have to go and write, I have to access memory and keep writing into it. Are you getting this? But on the other hand, if the write back cache, which is the state of the art today, I only write back whenever I am getting evicted. As long as I am not getting evicted or I am not getting invalidated, right, I do not really go and write back to this, okay, it will be there in the cache itself, okay. So this is this write back is also called as delayed write or lazy write. I am lazy to write into the memory, I will go and do it at a later point, okay. So this is a difference. Now please understand that that write back is more heavily practiced now, and with write back alone we can get that big performance. With write through we may not get that much big performance, but then there is an empirical thing, the amount of things that you read is much higher than the amount of thing you write, correct, right. So this is again, we can check this up, okay. The amount of loads is lesser than the amount of stores, sorry, it's more than the amount of stores. Load is read from memory, store is write into memory, okay. That you can see, right, even the amount you read and the amount of notes you write, right. Fine. So so write through and write back. So let us now concentrate on the other types of cache. See what happens here, okay, before going to that, let us see because of cache what is going to happen, okay. So one more point here. Now when in the example that I have talked here, I am talking about one single location, correct, okay. Now this write through policy is very good when I am talking of one location, but if you say I have a block, right, so today my granularity is not one location, right, what I fetch from the memory into the cache or what I write back into the memory, whatever I evict, that unit of transfer between RAM and the cache is not just one byte, it is one block. Now when I am looking at a block, then this write through will kill, because when I write into one location, I mean I am writing the entire block back, correct. So otherwise I should have an asymmetry, what I read is a block, what I write is a byte, okay. And imagine this, all these things is not a software C language program, but it should be you need a hardware to do this, so it becomes extremely difficult to construct or design such hardware, right. So this write through policy becomes a much more headache when I am looking at block caches, right, where my unit of transfer is a block from the memory to this thing and vice versa. While in the case of write back, that's pretty happy. So I will evict, whenever I evict I would have done enough changes in the block and then it's good that I evict. Okay, so this is extremely, this is one point that I wanted to tell here. Write through will not increase efficiency, write through is still there because at early stages people were not having proper mechanisms to actually address the cache coherency issue, right. The point is, so when I am really talking of some where will write through work, right. So this will be in some of the DSP processors we have seen write through, this digital signal processing processor, where there is very few writes, you keep only reading, right. So it's something like that's the reason why I came out with this reduction function. You read 100 numbers and you output one number, it's an addition sum of this, right. So DSP processors will have this fuse multiply add, A plus B into C, there is a multiplication plus an addition, So this is an operation. So then what will happen is you keep on reading, lot of things you keep reading, right, from the memory. And then multiple reads you do everything, but finally go and write only one. Right? So the number of loads will be phenomenally higher than the number of stores. Right? And that is the application for which it is destined for, the DSP process. That's the domain. So why should I break my head putting all this write back policy? See, implementing write back is going to be a nightmare. Just coming back, write back is going to be a very, very difficult implementation strategy. Right? And should I shoot this mosquito with a revolver, right? That's the question that comes when you go and look at DSP processes. I have few writes. Uske liye, so should I do all these stuff, right? Put to some heavy thing, look at LRU, all this nonsense. Why should I do? Let me go and write through. Okay, that's a very, that's the most intelligent decision you can take, right? I could also have actually disabled cache and just keep accessing everything from RAM, but number of reads are quite high. For example, I start doing a simulation, the number of repeated reads of a location is also high. Right? So I keep reading the same location again, right, for say some n iterations. But then finally I will only go and put one value back. Okay. So the reads to write is very, that ratio is very high. So these are the cases where your write through will work. Okay. Right. So DSP processors are some examples. I think Blackfin had Blackfin. There was a processor called Blackfin. Why I don't know, but name I don't know. Like why my aunt named me Kamakoti, like that, something like that. Okay. So Blackfin. Okay. You can look at Blackfin. Actually there you can even completely disable cache and use the cache itself like a memory. Okay. Okay. Some lot of interesting things can come. Okay. Fine. Now we will do some analytics. Yeah, I've been talking so much practice. So let me talk some theory. Okay, if you have an algorithm exam also this Sunday. So let me just talk some theory. So we have been telling that if I have a cache, I am going to get a lot of advantage. Okay. Now what is that advantage? Right? My memory access time is going to reduce. I can't say every memory access time. There will be some memory access where it is not in the cache, then I am going to get lot of, I am going to actually suffer quite a bit if the cache is not there. I have to go to memory and fetch it. But so the more, so if I take an entire program, the better way of assessing the impact of cache is to have this parameter, namely what we call as average memory access time. Or what we call as AMAT. Correct? I am interested in the average memory access time. If you take worst case, it will be worse. So I have to just go to memory and bring it, right? If there is a miss, then I have to go to memory and bring it. So that is going to be much costlier for me. And even when I want to read 1 byte, what I am going to read? I am going to read some 256 bytes. So the worst case memory access is going to be very large for me. So what I am interested is, overall I have spent some k times. Now I am interested in what is the total time spent by for memory access divided by the total number of instructions that access, total number of load stores, right? Total amount of memory spent for load stores. Total amount of time spent for load stores divided by the total number of load stores. That is my average memory access time. Okay. Now I have to look at, I have to get out with a very an expression for average memory access time in the presence of a cache. Are you getting this? Right? So why AMAT? Just not memory access time, but AMAT. Okay. Now in this context, let us go and see that what will happen. So this is a cache. I have an address with me and I do a lookup on this cache. Okay, lookup on this cache, whether it is there or not. So that will be, so how much time I will spend? I will spend cache access time, right? this is called, let me call it as, this is the cache access time, let me call it C or CT, C time, right. If it is not there, so if a cache hit happens, the time is C time, right. If it is not there, if cache miss means what will happen? I will go to the memory and fetch it from there, that is M time. So if there is a cache miss, what is the total time spent? C time plus M time. Okay.
About when we need to evict the page, then we need to.
Oh, that's included in that. That's included in that. We'll see that that is this memory time, right? So there will be some constant time, that memory time, because there will be, constant number of memory access. So we'll just take it as M time. Okay. So this is C time plus M time. So what is M time alone? This is called miss penalty. The penalty I pay, that is the extra time I spent because there was a miss, is called miss penalty. Okay, right? Now what I do is 90% of my memory access is a cache hit and 10% is a cache miss. Let us say that in the overall execution of all the memory access instruction, 90% of that was a cache hit and 10% is a cache miss. This 90%, which is equivalent to 0.9 and this is equivalent to 0.1, this is called hit ratio. This is called miss ratio. Let me call this as H, let me call this as small n. So your average memory access time is nothing but hit ratio into C time plus miss ratio into C time plus M time. How do you get this? Are you able to understand how I am getting this? How? So what is average memory access time? Total time for memory access divided by total number of memory instructions, correct? Okay. This is equal to total time of number of cache hit instructions into number of cache hit instructions into cache C time plus number of cache miss instruction into C time plus M time whole divided by total number of memory access instructions. Okay, because number of cache hit instructions, if there is a cache hit I would have spent C time there. So that is number of cache hit instructions into C time plus number of cache miss instructions, instructions which are not available, instruction or data which landed up with a cache miss, that would have spent C time plus M time. Now number of cache hit instruction by total number of instruction is hit ratio, number of cache miss instruction by total number of instruction is miss ratio, right. You got this? So this is how I derive this. A mat is equal to h into c time plus m into c time plus m time. This is nothing but h plus m into c time plus m into m time. What is h plus m? 1. So this is cache access time plus 1 minus h into memory access time. Okay. This m time is actually called as what? Miss penalty. So just to sum up, A mat is equal to cache access time plus 1 minus h into miss penalty. Okay, fine, got this? Okay. So just copy this. If you have any questions in this particular derivation, you may ask me. Now, because of cache, what could happen? So let us start with, let us go back to our pipeline. See, pipeline will not leave us till eternity. Okay. Now what are the 5 stages? Fetch the instruction, decode, fetch data, execute, store result. Now this type of an execution profile in your control unit, in your CPU, along with cache, when both of them coexist, what would be the issue? What would be the most show-stopping issue? Now you have done that assignment there, no? What did you do in fetch the instruction? What did you do in fetching the instruction? What will you do normally? Take it from and this, in this case, in our CPU, from RAM. From RAM means what? From, now in this context, after today's class, RAM means from cache. Okay, this has to access cache. Now you tell me, Kavya, now you know the answer. One stage is over, second stage, third stage. Just look at it. But then what happens? Next stage. This is decoding. Next stage, fetch data from where here? Cache. Who is fetching data when who is fetching what is fetching which? So can you just see there is some problem here? When I1's data is being fetched, I3 is being fetched. I3 as an instruction is fetched and I1's data is also fetched. From where? From the same cache. So what happens? Both fellows are trying to access the cache. Correct? Both fellows are trying to read from the same cache. That means there is a sharing of resource. And when I am sharing that resource, I have to now serialize it. So I should allow the first fellow to fetch data from the cache, then allow the, so there are 5 units, right? One unit is fetching the instruction, one unit is decoding, another unit is fetching data. So I have to serialize the action between fetching data and fetching instruction. Both cannot go concurrently. I have only one cache, I have only one interface. How can 2 fellows come and read from me at the same point of time? Are you getting this point? Yes or no? Right? What yaar? Are you able to follow what I am saying? Right? So how can these 2 fellows come and keep accessing me at the same time? Cannot. Right? So what sort of hazard it is? This is going to stop the pipeline. Because I have only one cache, I1 is asking for some data from the same cache, at the same time the fetch unit is saying fetch I3 from the same cache. Right? So there is a contention for the cache. right? So this type of an hazard is called structural hazard. Very good, right? The structural hazard we have seen earlier. I have when there is no execution unit, that I have 10 add instructions that I could execute together, but I have only 4 add units. So the remaining 6 has to wait. This is a structural hazard. But the structural hazard, another interesting case where structural hazard will come is that when I am implementing the pipeline, there will be one stage which is asking for a data, another fellow is asking for data, both fellows was asking for an instruction, and both fellows are attacking the same cache, and that will lead to a structural hazard. Yes? Yes or no? Right. So now, how do we solve this problem? There you go into what we call as a split cache. What is split cache? Nothing great. So what I do, I have one cache called I cache, another thing called D cache. What is I cache? Instruction cache. D cache, data cache. So if I fetch data, I will put it in D cache. If I fetch instruction, I will put it in I cache. So I and D may not, I and D will not even be same. So instruction cannot be data, data cannot be instruction. Right? So when I do the fetch, when I do the fetch, I fetch only from the I cache. When I do a data, I fetch only from the D cache. So these two are accessing two different caches, and hence this structural hazard is avoided. Okay? Is it fully avoided? Yes sir, what one? Go and see, there are more stages I have written there. I1 is storing and somebody is fetching data. So that is why this D cache will be a multi-ported cache. One is a read port, another is a write port. So this D cache normally will be a dual ported graph, PORTED. It will be a dual ported cache. Dual ported in the sense that one port can be a read port, another port can be a write port. Right? Now what is the problem when I have a dual ported cache?
Data dependent.
There will be data dependence. Obviously, right? When this fellow is trying to read, this fellow is trying to write, both are reading and writing from the same location, there will be a data dependency. Now there is another way by which it is actually handled. This is actually a data hazard, where I am writing and he is reading. Right? So this is a read after write hazard, and we have already know how we are handling read after write hazard. But when I am looking at memory, when I am looking at cache as a separate entity, because today cache is a separate block, I can make an IP and keep selling that IP, I have to look for this. So how will I solve this problem? When there is a tie, I will give preference to the write. Correct? It is obvious, because every time I read, I want to get the latest value of the location. So when there is a write and a read for the same location, I will give preference to write. So that is how dual ported caches are built. So what we have seen now, I have a I cache and a D cache. Why did I split it? Otherwise, in a pipelined environment, I will get a structural hazard. Okay? Now, the next step is that even after I split it from I cache, I split it into I cache and D cache, again I will have an issue between the fetch data and the store result stage. Correct? The way I handle that is by having a dual ported cache. And in this dual port, again I make a story saying that, not story, it is a reality, that I should have higher preference for write when I read and write from the same location. Okay? Why do you give preference to write? Because let us say I am writing into 1000. So I1 is writing into 1000, I3 is reading from 1000. What should the value of 1000 be? It should be I1's result, right? because always when somebody is writing, he will be an instruction before you. So between a write and a read, I have to give preference for write.
Can't you use something like a reorder buffer?
Yeah, those things are there. So that's what I am saying. If you keep the Tomasulo algorithm that we had already seen, then this type of resolution itself is not necessary, because there itself this read after write would have been recognized, and the hardware would have stopped it. Okay, but when I am generating a cache is an intellectual property block, IP block. Okay, so this cache is also an intellectual property block. So people make caches separately, independent of how the CPU is done, and they sell it. So they make money. Okay. Now when they do such a thing, then they have to handle this, because they may give it to a dud processor, right? They may not give it to a intelligent Tomasulo processor. They may give it to some stupid processor which will not handle all these type of things. So then when it comes, then the cache has to handle. Okay. So every stage we will put these type of safeguards to see that your program ultimately gives the effect of having be executed in the way it is listed, what you call as the program order. Okay. So that is why even though when we give a dual ported cache, write will be given more privilege than read, right. So if there is a tie between write and read, write will happen first, then read. Okay.